Good morning, everyone. Welcome to my talk, Apple PAC 4 years later. I will share my research on reverse engineering PAC hardware implementation on Apple M1. And this talk is a technical talk about Apple CPU feature, and I hope you enjoy. So let me first introduce myself. My name is Zechao. It's difficult to pronounce it, but don't worry, you can call me Zach, or my English name, Zachary. Yeah. Currently, I'm a master's student at Zhejiang University. My research focuses on operating system security, reverse engineering, and virtualization. And also, we have some other team members, Jiaxun, Yutian, Wenbo, and Wang. So let's get started. Here's the outline of my talk. First, I will introduce what is PAC and the current state of Apple PAC research. And second, I will introduce how I reverse it by solving two challenges. And the final part, the most important part of this talk, is our findings on Apple PAC hardware implementation. So let's get started. And first, let's take a look at the basic memory attack. Here's the simple example of pointer's life cycle. Typically, the pointer will be stored into memory for some reasons, and then you will be loaded out from memory and used to do function call or memory access. Therefore, attackers often target the pointer stored in memory. By corrupting the pointer, they can hijack the control flow, data flow to do further attack. So how Apple mitigate this attack? It comes up with pointer authentication. Pointer authentication, or PAC, is a hardware feature for protecting the pointer's integrity. Pointer authentication provides PAC instruction and alt instruction. PAC instruction can generate the signature based on the pointer and the PAC keys, and then you will store it into the higher unused space of the pointer. With pointer authentication, if the attacker tries to modify the pointer, that will be detected by alt instruction. Alt instruction will validate the pointer by regenerating a signature based on the current pointer value and compare it to the one stored in memory. Yeah. Note that even the PAC or the signature is also stored in memory, but the attacker cannot forgery a valid signature easily because they don't know the key. And now, let's dive into more detail about pointer authentication. Pointer authentication is a hardware feature introduced in UNBA.3 specification. It provides 5 128-bit PAC keys, and each key is made up by 2 64-bit system registers. Note that these system registers can only be accessed under the privilege mode. There are 4 keys for signing the pointer, including APIA, IB, DADB. Besides that, there's an APJ key for general usage, like generating a signature. For the PAC instruction, it will take 3 inputs, the key, pointer, and modifier. And then it will generate the signature based on these inputs and store it into the higher unused space of the pointer. For the PAC keys, and it's worth noting that in the ARM specification, there's only 1 PAC keys for all exception level. In other words, the PAC keys won't change even if you change the exception level. Besides that, ARM provides a per key switch to enable or disable the PAC instruction. If you disable it, the PAC instruction will work as a NOP instruction. So these are what we need to know about the pointer authentication in ARM specification. Now let's head into the Apple PAC. Apple implements pointer authentication on A12 chip for iPhone XS in 2018. After that, this hardware support is deployed on all Apple silicon-based devices. Since 2019, there are a lot of incredible research works on Apple PAC protection. For example, like Brandon from Google Project Zero and Tim Pangu, and etc. But if you look into the research work on Apple PAC in the past few years, you will find that most of the research work are focusing on software or how to bypass the PAC protection. In contrast, for the hardware side, there's only one research work has mentioned this part. It's the blog written by Brandon Azad in 2019. In this blog, he mentioned that the PAC instruction behavior on ATF chip is significantly different from the unspec one. He termed this instruction behavior as dark magic, and this dark magic makes the Apple PAC can mitigate cross-domain attack without software support. So, and I will explain later about what is cross-domain attack. But here we can see that in the past 4 years, there's no follow-up work for this dark magic. So that's the main motivation of my research, and I want to find out the implementation behind this dark magic. Now, so let's take a recap of what is dark magic or cross-domain attack mitigation. So first, let's start with cross-domain attack mitigation. What is cross-domain attack mitigation? And basically, it's a pointer substitution attack across different domains. And why it is feasible? Because PAC does not provide any hardware isolation for differentiating the signature generation in different domains. In other words, if you generate the signature with the same inputs in different domains, the signature will be equal. So the attacker can try to forgery a side pointer in one domain and then use that pointer to substitute the pointer in other domain. And finally, hijack the control flow or data flow in another domain. And know that the attacker-controlled side pointer can also pass the authentication in victim's domain because the signature generation process in different domains are equal. And let's take an example. Like here is the cross-EO attack. The attacker can generate a side kernel pointer in user space and use it to replace a real side kernel pointer. And then finally, hijack the kernel control flow or data flow. So how to mitigate the cross-EO attack? Well, if you use the unpack to protect the kernel, there are two solutions for mitigating this attack. The first one is to maintain different key values for user space and kernel space. And second one is to disable the user space PAC. So back to the dark magic, what Brandon discovered is that even there's no key switching operation in the SU kernel, the signature generated with the same inputs in user space and kernel space are different. Yeah. Besides that, there are some other cross-domain attack mitigation on Apple PAC. And the second one is cross-key attack. That means if you set up all the PAC keys with the same values and then generate the signature using different keys with the same inputs, the signature will be equal if you are using the unpack. But for the Apple PAC, it's different. The third one is cross-boot attack mitigation. If you use the unpack and set up the keys with the static value for different CPU boots, the signature will also be static. But for the Apple PAC, it's different. Okay, the final one is cross-VM attack mitigation. We discovered this one on Apple PAC. And as I mentioned before, in the ARM specification, there's only one set of PAC keys for all exception level. So if you set up the keys in virtual machine or hosted machine, and hosted machine with the same values, for the unpack, the signature generated in virtual machine and hosted machine will be equal. But for Apple PAC, it's different again. So here we have a conclusion, is that Apple implements the dark magic or cross-domain attack mitigation without software support. And therefore, I want to find out how Apple customized the PAC hardware to achieve this dark magic. And here I make you a promise, is that after this talk, you will know how Apple implements it. So let's head into next part, reverse engineering. how I reverse engineer Apple PAC? Well, the basic idea is simple. It's to change the CPU states and see what happens. The CPU states here means different configurations of CPU features. And in the ARM VA specification, the CPU features are controlled by system registers. So step 1 is to set up the system registers, and the step 2 is to run instructions and see the result. So for the step 1, it comes up with challenge 1. Is that what are the system registers we want to set? Because Apple introduced a lot of new system registers, and there's no official documentation about these system registers. And then for the step 2, there's also a challenge. Is that how to read the PAC key? Because I discovered that Apple implements hardware PAC key protection to prevent the PAC keys from being read. And I will explain later about what it is and why we need to bypass it. So for the challenge 1, we have task 1. We need to identify Apple's PAC system registers. Also, for the challenge 2, we have task 2. Is we need to bypass Apple's PAC key protection. So let's start with the task 1. Identify the Apple's PAC system registers. And let me first introduce what is system register. And system registers are registers for configuring the CPU feature. It can be accessed using MSI instruction and MIS instruction. For example, like this instruction is used for set up base address of the kernel page table using the value in X1 general register. But for better understand the technique we will discuss later, here we need to clarify something. Most people may think that the TTBL1U1 here is a register, but actually it's not. In the ARM specification, the exact meaning of the TTBL1U1 is a mnemonic for an encoding. And here we don't need to understand the meaning of each bit of the encoding. We can simply regard it as a combination of some numbers. So back to the MSI instruction. The exact meaning of the instruction is that the MSI instruction will use the encoding to access register. Why we need to clarify this? Because actually the encoding and register, they are not one-to-one mapping, which means different encodings, they can be used to access the same register, and also one encoding can be used to access different registers on the different CPU states. With this knowledge, we can better understand another feature, the system register redirection. System register redirection is one of the hardware supports of virtualization host extension, or VHE. VHE is a set of hardware supports for enabling the operating system to run on year 1 and year 2 exception level without software changes. It's worth noting that the VHE is hardwired on Apple M1. In other words, it's implemented and is always enabled on Apple M1. Among these hardware supports, the most important one for our analysis is the system register redirection. So what is system register redirection? Basically, it contains 3 things. First one is banking the register in both year 1 and year 2 exception level. At the same time, there will be a year 2 encoding for accessing year 2 register. The second one is access redirection for year 1 encoding. As shown in this pack, using the year 1 encoding on year 2 exception level, the register which will be accessed is the year 2 register. The third one is year 1-2 encoding, which can be used to access the year 1 register from year 2 exception level. These are the background we need to know about the system register. And for better understanding, I term the EO12 and EO2 encoding as alias encoding. So back to the Apple PAC system registers. What Apple have done is that Apple introduced a lot of new encodings to access new registers to control new features. However, Apple does not provide any documentation about it. If you look into the binary for these system registers, all you can see is only a bunch of numbers, and you have no idea what it is and how to use it. It's worth noting that there's a tip here is that the CRN field of the Apple PAC encoding is always 15 on Apple 1. So you can easily determine which encoding is Apple PAC 1 or ARM PAC 1 by looking this. For task 1, we want to answer these two questions. The first one is how to identify encoding of interest. Second one is how to understand this encoding. About identify or document the Apple PAC encodings. There are already some incredible works done by Azad, and they have documented a lot of Apple PAC encodings. However, the method of how to document them is not well described. So here, I'd like to share my insights on how to document them. And I found that some of my insights are also shared by Azad. So the first tip is that you must look into binary. Although Apple open sourced the SL kernel, the code related to Apple PAC system registers can only be seen in binary. For example, as shown in this two picture, they are the same function for texting the PAC functionality, but the checks of Apple PAC system registers can only be seen in binary. So if you look into binary, you can document the encoding based on the string data or functions. The second tip is that I recommend you to identify the alias encoding because it's really useful when you are doing tests. I will give you some example later. For the alias encoding, we can identify them based on the system register redirection feature. And here's an example of identifying the PAC-C EO12 encoding, which is introduced by Apple. First, we can set up the EO1 register using the EO1 encoding at EO1 exception level. And then we can test all possible encodings on EO2 exception level to identify that if there's another encoding that can read out the value we set before. So that encoding will be the EO1 encoding, EO12 encoding. And similarly, you can use this method to identify EO2 encoding. But here's the thing is that this method is not applicable for all cases. For example, the PAC-key EO2 encoding, I identify them in a more specific way, and I will explain later. Yeah. And the tip 3 here is you can try to identify more encoding based on the alias encoding you identified before. For example, for the VMDIF encoding, there's no information in binary, indicating that this encoding is PAC related, but we mark it as PAC related because it's initialized with the alias encoding we identified before in the same basic block. And also, I did some tests and confirmed that this encoding is PAC related. But the second question is how to understand the usage of this encoding. And the first tip is that you can do some manual analysis, and it's easy because some of the registers are set up with hard-coded value or static value. But for other cases or more complex cases, I recommend another method. It's dynamic analysis, or in other words, you can sniff or monitor the system register. We can do this because we implement a hypervisor-based kernel debugger. And we implement two functionality which are not supported by the official kernel debugger LLDB. The active kernel debugging and unlimited number of breakpoints. And this tool is very useful when you are doing an analysis of SM kernel. And yes, we plan to open source it this year. And this work is a co-work with my friend Jiaxun. And you can follow his Twitter here. And if you have any question, feel free to reach out. Yeah. And the tip 3 is that you can run your test on your one exception level first. As I mentioned before, the VHE is hardware on Apple M1. So most Apple spec CPU features are deployed on both your 1 and your 2 exception level. Running your test on your 1 is a very useful trick because you can trap to your 2 exception level and observe your 1 hardware with a higher privilege. And I will give an example later. Yeah. So here we finish the task 1. However, I need to say that the cases I mentioned before, like documented encoding based on string data or text functions, and these cases are easy or general, and most of cases has been done. But I discovered that there are still a lot of Apple spec encodings remain undocumented, and even some encodings are not used in SM kernel. So if you are interested in this, we need your help for more tests to document them. Yeah. So let's head into the task 2. Bypass Apple PAC key protection. First, there are 2 PAC modes on Apple M1. The unpack mode and Apple PAC mode. Under the unpack mode, the PAC instruction behavior will work as in ARM specification. And the Apple PAC mode can be enabled by setting up a bit of Apple spec PAC system registers. And know that once you enable it, it cannot be disabled. The SL kernel will enable the Apple PAC mode during kernel boots. So our target is to provide the PAC instruction behavior after enabling Apple PAC mode. So what is PAC key protection? For example, if we use the EO1 encoding to read the key register under the unpack mode, we can read out the key successfully. Yeah. But once we enable the Apple PAC and try to use the same method to read out the key, there's only an exception waiting for you. Yeah. So why we need to bypass the key protection? Well, let me explain our situation in reverse engineering. For now, there are 4 inputs we can control. The first one is the key value set up using your 1 encoding. The second one is the key selection, or we can choose which key we want to use for signature generation. And then is pointer and modifier. However, the output we can read is only the PAC result or the signature. So as we can see, there are 2 processes between the inputs and outputs. As a result, even we can confirm the existence of the dark magic by reading the signature, but we cannot determine the dark magic is happening in which process. And yeah, so that's why we need to read out the key, because once we can read it, we can determine the dark magic is happening in which process and do some further reverse engineering. Yeah. So I found that the PAC key protection is deployed on both your 1 and your 2 exception level. For both of them, I propose 2 methods to bypass them. Yeah. The first one is for your 1 key protection. As I mentioned before, I recommend you to run the test on your 1 first, and also to identify the alias encoding. I mentioned that this trick are really useful And I will show you an example. So here is the example. I found that although we cannot read out the key value using the EO1 encoding, but for the EO1 key protection, we can bypass it by reading the key register using the EO12 encoding on EO2 exception level. Yeah. So what about the EO2 key register? No. It's what about the EO2 key protection? Yeah. How to bypass it? Because now there's no higher exception level or EO3 on 8.1. The method we used for bypass the EO1 key protection is not applicable for EO2. So my first idea is that are there some other encodings for access the EO2 key register? And the answer is yes. There are EO2 key encodings for accessing the EO2 key register. However, unfortunately, these encodings are also non-readable. Yeah. And then I came up with the second idea is that if I can use the side channel attack to lift the key values from register, I did some tests. I found that the side channel attack works on 8.1, but it can only work for leaking the things from memory. For the system registers, it fails. After that, I did a lot of tests. Unfortunately, I still cannot directly read the key register out. But luckily, I have some observations. Observation one is that I discovered that if the Apple PAC mode is disabled, there's only one set of PAC keys available for signature generation. This phenomenon makes sense because, as we mentioned before, in the ARM specification, there's only one set of PAC keys for all exception levels. But once we enable the Apple PAC on EO2, the access of using the EO1 encoding on EO2 exception level will be redirected to the EO2 key register. Observation 2 is that enabling Apple PAC will not change the value in EO2 PAC key register. Besides that, observation 3 is the PAC instruction will generate the signature based on the key value accessed using EO1 encoding. Yeah. And back to our situation of the reverse engineering. What we need is when we want to determine the PAC key value used for signature generation when Apple PAC is enabled. So combining the observations and the ability we really want, I came up with the idea to bypass the EO2 key protection. We can preset the PAC keys before Apple PAC is enabled. So there are only 2 steps we need to do. Step 1, we can set up EO2 PAC keys using EO2 encoding with the value. And then enable the Apple PAC. The PAC instruction now will generate the signature based on the value we set before. So the task 2 is also finished. After solving these 2 challenges, what we need to do is do some experiments and summarize the findings. So here's the final part. And the most important part of my talk is our findings on Apple PAC hardware implementation. And here's the finding overview. Our findings contains registers and instruction behavior. And I will introduce the register first, but the functionality of them will be discussed in detail, combining our findings on instruction behavior. So Apple introduced 3 new PAC system registers. First one is a control register. And second one is a 128-bit key for differentiating the signature generation between user space and kernel space. The third one is a 128-bit diversifier to differentiate the signature generation or the PAC instruction between virtual machines and host machine, and even between different virtual machines. So let's start with the key access instruction. As I mentioned, each PAC key is made up by two 64-bit system registers. So there are two system registers indicating the lower 64-bit and higher 64-bit of the PAC keys. And here we can see that if we set up the lower 64-bit and read out the key, and actually there's nothing happen. What you read is what you write. But when I try to set up higher 64-bit, something happens. Yes, the key is totally changed. And I did some tests and confirmed that the key now in the register is the key value used for signature generation. So the first finding is that if we set up the higher 64-bit of the PAC key on the Apple's PAC mode, it will trigger a key transformation. And then I did some more tests on EO1 key transformation. I set up the VNDF in different values and trigger the key transformation. And the result shows that the VNDF EO2 is one of the inputs for EO1 key transformation. Besides that, I discovered for the same inputs and the key transformation result for different keys are different. So how Apple differentiate the key transformation result for different keys? I won't find out what it is. And after a lot of tests, luckily I found it. Yeah. Here's the key transformation result after I set up the VNDF from 0 to 7. And it's difficult to read, but don't worry. If we put some color, it will look like this. So you can see that there's a symmetry here, and I give you the answer of it. Is that there are 6 per key sorts for differentiating the key transformation for different keys. And more importantly, for the EO1 key transformation, the per key sort will do an XOR with VNDF. And the result will be one of the inputs for EO1 key transformation. So let's take a summary. Let's have some summarize of the inputs and outputs for EO1 key transformation. Is that there are 4 inputs for key transformation. First one is the lower 64-bit of the key register. And second one is the operator of the instruction for setting up the higher 64-bit key. And the third one is the result of per key sort XOR with lower 64-bit of VNDF. The final one is the higher 64-bit of the VNDF. And the output of the key transformation is the real 128-bit PAC key for signature generation. In addition to that, I confirmed that the key transformation is also deployed on EO2 exception level. For the EO2 key transformation, there's a per boot diversifier to differentiate the key transformation for different CPU. For the PAC instruction, I found that Apple introduced an extra key to XOR with the PAC keys before signature generation. And this extra key can be enabled in user space or kernel space by the Apple's PAC control register. For the PAC algorithm, I found that the PAC algorithm on Apple is not the comma recommended by ARM. And there's an interesting thing is that the result of the modifier XOR with the key value will be one of the inputs for PAC algorithm. Besides that, I discovered that Apple introduced a new per-EL switch to enable or disable the PAC instruction. And this switch can be cooperated with the ARM stack per key switch. And if one of them is enabled, the PAC instruction will be enabled. So let's summarize how Apple implements the dark magic or cross-domain attack mitigation. For the cross-email attack, I found that the SEO kernel only enabled the actual key on user space. As a result, the signature generated in user space and kernel space are different. For the cross-VM attack, Apple introduced two different diversifiers to differentiate the key transformation result in virtual machine and host machine. So, and also for the cross-boot attack, Apple introduced a per-boot diversifier to differentiate the key transformation for different CPU boots. Finally, for the cross-key attack, Apple introduced per-key sort for differentiating the key transformation result for different keys. And meanwhile, I also do some reverse and summarize the key management in the SEO kernel. And we can see that the SEO kernel will configure the API DAGA with a global or static value. And while it will initialize the API BDB and extra key with a per process value. As a result, the PAC instruction scope on the SEO kernel looks like this. For the PAC IADAGA, they are global in kernel, but they are per process in user space. For the PAC IBDB, and they are per process. And for some process, the SEO kernel will disable the user space PAC by disabling the per key switch. Yeah. So let's summarize the limitation of my work. And yes, there are still things we don't know. The first thing is that what's the algorithm used for key transformation? And also, what's the PAC algorithm on Apple 1? And besides, although we can confirm that how the per boot diversifier works, but how Apple implements it is still a question. Yeah. By the way, I think that maybe we can look into the bootloader to see that if there's some useful message. Yeah. So here's the summary of my work. Yeah. Although there are still some implementation remain unknown, but the design of Apple PAC is clear. Apple's PAC hardware design looks simple, but it's insightful. Among all the ARM CPU vendors, Apple is definitely the leader in Pointer Authentication. So for how to improve this hardware to protect the system, the whole system, and here's the answer given by Apple. I think that other ARM CPU vendors and even ARM can learn a lot from this design and try to improve the Pointer Authentication in the future. Okay, so yes, there's one more thing. Is that I also did a security analysis of kernel PAC protection, and one of my findings got a CV from Apple. And however, this talk is about our findings on how Apple implements the PAC hardware and not about how to bypass it. So if you are interested in that part, you can check out my using security paper. Yeah. Okay, so this is my talk. Thank you for having me, and thanks to Black Hat for giving me a chance to share this work with you. And if you have any question, feel free to reach out on Twitter or email. Yeah, and I will answer that. And thank you.